In this video, we're going to look at section 2.2. So previously in chapter 1, what we talked about was we had some population, which was a group of people or things or animals that we'd like to learn about, but usually inspecting the entire population is very difficult. So what we need to do is to take a sample from that population, and our goal is going to be to use that sample to say something intelligent about the population. Well, usually what we're going to do is we're going to collect data from that sample. So if we're going to use the data from the sample to say something about the population, we need to be able to summarize that data. And so in section 2.1, what we're going to look at is going to be how to summarize categorical data. In 2.2, we're going to focus on what are called quantitative variables. And so when describing a quantitative variable, we're generally going to consider the following three questions. We want to know the shape of the data. In other words, if we make a plot of it, what does it look like? Where are those data values centered at? And how do they vary? Are they really spread out, or are all the data points really close together? These are all aspects of what we call the distribution of the data. So when we talk about the distribution, we're really looking for a way to summarize all three of these questions. And so that's what we're going to start talking about, is the distribution of a data set. So one of the most common ways to visualize the shape of the data set is through what's called a dot plot. And so in a dot plot, what we do is for each and every data point that is in our data set, we plot them where each data point has its own dot. And so looking here, if we had the data set in front of us, you can think of an Excel spreadsheet here. And what this data set is, as it tells us by the title, this is the world gross for all 2011 Hollywood movies. Every one of these movies has its own individual dot. And so looking here, we can see that some movies earned close to zero or at zero, where some movies earned quite a bit of money up here. So an outlier is an observed data value that is notably distinct from the other values. So in other words, if all of our values are really close together, are there any that kind of stand apart from the other ones? And so if we look again at that world gross for the 2011 Hollywood movies, notice that these three data points here kind of stand apart from the other ones. So these three are what we would consider to be outliers. And it just so happens this movie up here, this was Harry Potter's and the Deathly Hallows Part 2. This one was one of the Transformers movies. And this movie right here was Pirates of the Caribbean on Stranger Tides. And so all three of these were blockbusters. They earned a lot of money, and they earned up so much money that they were kind of far away from these other data points. And so again, we would call these outliers. Now another common plot that we could look at is what is called a histogram. And so a histogram, what it's going to do, instead of having dots for each of the data points, it's going to draw a bar that is the height of the number of data points that falls within a certain width. So if we look here, if we're looking at the world gross, and these are done in millions, if we wanted to know how many of these movies earned between 0 and 200 million, we can see that that's a little over 100, maybe about 120 movies. Whereas we probably only had one movie that earned between well, remember again, these are in millions, but that earned in this category, and remember that was the Harry Potter. So on the dot plot, we had one dot. For the histogram, we're going to have a bar with a height of 1 here. And so the histogram and the dot plot both contain the same information, but they summarize it in slightly different ways. Now, for the computer project 1, you're going to focus on histograms, and you're going to look at how to use a histogram to summarize data from a population as well as from a sample. Now, in 2.1, one of the plots that we're going to look at is a bar chart, and bar charts look very similar to histograms. So really quickly, we want to look at the difference between a bar chart and a histogram, since they do look so similar. The biggest difference is that we make bar charts for categorical data and histograms for quantitative data. The other visual difference is that for a histogram, the bars touch, whereas in a bar chart, they are separated. So that's the difference between a bar chart and a histogram, and they do look fairly similar. Now remember that one of the questions we wanted to ask about the distribution is we wanted to look at the shape of the distribution. So we've got some different terms or definitions here that we're going to use to describe the shape of a plot. The first one is symmetric. And so a symmetric plot, you can imagine if you took the plot and you held it in your hands and you folded it in half, if the plot looks the same on either side, then that's what we call symmetric. You can imagine if I looked at a plot and I grabbed the right side of it and I pulled that right side out, that's what we call right skewed. And we'll look at a picture here in a minute. And so what this means is that all the data is piled up on the left, and the tail of the data, in other words, we've got a few stragglers that are out to the right. That data set has been pulled out to the right. Left skewed is similar, except now all the data is going to be piled up on the right side, and then it's going to be pulled to the left. And then finally, if the data is symmetric and has a bell shape, then we call it bell-shaped data. And there's many other possibilities, but these are going to be the ones that we're going to focus on. So let's look at some examples. So here are 3 different plots. The first one is what we would call symmetric and bell-shaped. Now with real data, we're never going to get a perfect plot. So if we took and we drew a line right here and we folded it in half, I know that that plot isn't perfect on either side, but it's pretty close. And so that's why we're going to call this one symmetric, and then it's bell-shaped because notice I could kind of draw a bell over top of here. So that's symmetric and bell-shaped. And again, with real data, these shapes are never going to be perfect. Now the next one here, notice that most of the data points are piled here on the left, and it kind of looks like somebody grabbed the data and pulled it out to the right. When we pull the data out to the right, that's what we call right skewed. Most of our data is on the left, but the data's kind of been pulled to the right, and we've got a few points out that way. Now notice this one has a similar shape in the sense of we've got all of our data piled to one side, but now all of the data is piled on the right side and has kind of been pulled to the left. So this is what we call left skewed. Now notice that each of these 3 plots, these are different histograms, and we could use different shapes to describe these different histograms. Now sometimes when describing a histogram or a dot plot, what we could do is we could think of drawing a smooth curve over top of the plot. So notice we've got a dot plot here, and this dot plot is symmetric and it is bell-shaped, so we call it a bell-shaped curve. And we could think of summarizing this dot plot by drawing kind of this nice smooth curve over top of it and then only looking at the curve. Now, doing this is going to become very useful later on in the course when we get to Chapter 5, so just kind of keep this in mind that one way to summarize these dot plots in this histogram is we can think of the overall shape that these plots take. And so if we just thought of the overall shape that they take, we could also draw out these different shapes, and then we would describe them using the same language as when we just looked at the histograms. So notice for this curve, again, most of the data is piled on the left, and it kind of looks like the curve has been pulled out to the right. So we call this right skewed or skewed to the right. For this one, the data is piled on the left, and it looks like someone kind of pulled it out to the left. So that's skewed to the left. Again, here's another symmetric bell-shaped. Now notice here that not all symmetric distributions have to be bell-shaped, and this last one's a good example of it. Notice if I kind of drew a line down the center and I folded it in half, either side of this shape would look the same, but this thing is not bell-shaped. So for this plot, I would call it symmetric, but not bell-shaped. Now, one of the other things that we'd like to look at when we describe the shape of a distribution is we want to talk about the center of the distribution. In other words, where are most of our data points clustered at? And one of the most commonly used statistical summaries is known as the average or as the mean. And so here is the formula. And don't get too hung up on the formula here. All this formula is saying is you're going to add up all of your data points and then divide by the number of data points. And so this is the same average that you saw, long time ago in middle school or elementary school. This is the exact same formula. It's just now we've used a little bit more formal notation for it. But again, we're still looking at the same average that you've seen, in the past. We're looking at adding up all of the data points and then dividing by the number of data points. Now, remember that before we talked about outliers, where outliers are these data points that are away or kind of set farther away from the other data points. And we saw that in those Hollywood movies. Well, it ends up that when we look at the mean can be heavily influenced by those outliers. And so we say that it is not resistant. And so a resistant measure is going to be a measure that does not respond strongly to changes in a few observations, and we call them robust when they are resistant. So an example here is, you can imagine, let's say I had a group of people in the room, and I was interested in the average amount of money they make per year. And we'll just say that I've got everyday people in the room. Well, you can imagine if Bill Gates walked into that room and I recomputed the average, that number would drastically change. And Bill Gates is also an outlier because we know that Bill Gates makes a ton of money every year. He's not like you, your everyday person. So that's an example of how an outlier can be introduced. So if we introduce Bill Gates' income, then the average income of the people in the room is going to drastically change. In other words, that average is not resistant to the outlier of Bill Gates. Now, recall in Chapter 1 that it's important to distinguish between a population and a sample, and we're going to use notation to distinguish if a mean is calculated from a sample or a population. Now, when we come back to class on Tuesday, you're going to have a quiz over this right here. So anytime we calculate the mean from a sample data set, we're going to denote it as X bar, and that reads X bar. You see it's just got the little line over top the X. Anytime we calculate a mean for population data, we're going to denote it with the Greek letter mu. And so for your quiz on Tuesday, you're going to be able, if I give you a scenario and I say, hey, I'm going to calculate the mean from a sample data set, you're going to want to be able to tell me, well, the symbol you're going to use for that is X bar. Whereas if I calculate a mean from a population, then the symbol for that is going to be mu. Now, another common measure of centrality besides the mean is what we call the median. And how the median is calculated is you order your data from smallest to largest, and whatever the middle data point is, that's what we call the median. And now, one of the reasons we may want to use the median instead of the mean is that the median is resistant. It's a resistant measure of centrality. And so what we mean by that is if we introduce an outlier to the data set, it's not going to have a strong effect on where the median lies, where it may have a strong effect on the mean. And so the last thing we're going to look at here is we're going to look at a symmetric bell-shaped distribution, a left-skewed distribution, and a right-skewed distribution, and we're going to compare where the mean and the median fall for each of these. Now, if we're looking at a symmetric distribution, it ends up that the mean and the median are equal to one another. In a left-skewed distribution, it ends up that the mean is going to be less than the median. And the reason for this is in a left-skewed distribution, notice we're going to have some more data out here on the left because the data has been pulled this way. And these data points out here are going to have a strong influence on the mean. In other words, they're going to kind of pull it to the left. And then for a right-skewed distribution, we see the opposite effect. Notice that the mean is going to be pulled upward by these data points out here on the right. So we end up with the mean being larger than the median. So one caution that you need to have here is a comparison of the mean and the median alone is not going to tell us about the shape. You're still always going to have to plot your data to be able to figure out what the shape of the data or the shape of that distribution is. And so that's going to conclude section 2.2.